What is a vector field? So imagine that this is the bottom of a river and then perhaps there's some hill or something like that. So as the water flows, let's say the water's flowing this direction, right here, it could be going pretty fast, so that would be a big vector. And then as it hits this little hill right here, it's going to slow down, so the vectors will get smaller. And perhaps some of them will go up like this. Some will go down like this. Some might even create what's called an eddy and go back around like this. Well, if you look at all of these red vectors and then you had that for every possible space or possible point in the river, all of those little vectors, that's a vector field. Usually given by a function. Let's say, for example, the function at the point x, comma y, comma z. So that's just saying take any point in space and then put a vector there. And this one is going to be as simple as possible. It's just going to turn it into the vector x, comma y, comma z. So that would mean here's the x, y, z system. When you're at the origin, this would be 0, 0, 0. So the vector is 0, 0, 0. So that's just a point. Now, if you're at some point like 1, 1, 1, then the vector is going to be 1, 1, 1. And that vector has a length of square root of 3. It's not that big. And so when you're close to the origin, you would get these vectors that are pointing out and they're not that big. But the farther you go out, when you use, for example, a 2, 2, 2, that vector is going to be longer. And then as you go out, the vectors are going to get longer and longer. And they're all pointing out from the origin. So this could be something like the Big Bang. Everything started at this point and then starts to expand faster and faster and faster. So that is a vector field. I know, I thought we were going to integrate also, but just a moment, there's a few other things we need to do first of all. And then one is real quick, just a reminder of the gradient. So let's say that f, so notice that capital F gives you a vector. Lowercase f, this is just some kind of function in three-dimensional space or even four-dimensional space. Let's say that it's this. So if you plug a number over here on this side and then you square both sides, you basically get a sphere. So these are different spheres. And find the gradient. So the gradient of f is a vector. You take the derivative with respect to x, you take the derivative with respect to y, and if you have it, take the derivative with respect to z. So we're basically taking a surface and then we're creating a vector field. So let's see, the derivative with respect to x. Since it's the square root function, the derivative is going to be 1 divided by 2 times that square root function. And then do the chain rule. Take the derivative of the inside, which would be 2x. And then these little 2's could cancel. Likewise, when I take the derivative with respect to y, the only difference is this is going to be y. And when I take the derivative with respect to z, then this is going to be z. So in other words, the gradient, which is a vector field, would be x divided by this square root. Next it would be y divided by this square root. And next it would be z divided by the same square root. or I could write it like this. Since they're all divided by the same thing, I could just say the whole thing is divided by that square root. And there, we've created our very own vector field. Now on to the next idea in this section, work. How much work does it take to pick up a 5-pound object? Well, work is force times distance. So if it was a 5-pound object and you pick it up 1 foot, then you've done 5 foot-pounds of work. Now let's say that F is this vector field, and the components are going to be M, N, and P. And then suppose that R of T is going to give you the path that it goes along. Oh. And then that's for T going from A to B. And one other thing is this is supposed to be a smooth curve, so it can't be like this, it can't have any holes in it, it can't have sharp points like this. It's just which most curves are that we're dealing with. Nice smooth curve. So then work. So if this was the amount of force, and then this is the path that you're following, then the work is going to be multiply those two in the form of F dot product, the derivative of R with respect to T, and then we'll integrate with respect to T, with T going from A to B. So in other words, it's going to be integrate from A to B, the F function, which is M comma N comma P, dot product with the derivative and then integrate from A to B. So for example, number 3, so the force is given by this function, this vector valued function. And we're just keeping it simple for right now. So then find the work along this path. So it's going to be T squared, T to the 4th, from the origin to 1, 1, 1. So this means T equals 0, because then it would be 0, 0, and 0. And this one means T equals 1. So we're going to be integrating from 0 to 1. So work will equal integrate from 0 to 1. So take this function, but then you can substitute that this is X, this is Z, and this is Y. So it'd be X gets replaced with T, Z gets replaced with T to the 4th, and Y gets replaced with T squared. And then dot product that with the derivative. So the derivative is going to be 1, 2 times T, and 4T cubed. And remember, the derivative is also the velocity vector. All right, so what do we got? So we have T times 1. We have T to the 4th times 2T, so that means plus 2T to the 5th. And then T squared times this one will be 4T to the 5th. All right, now just integrate from 0 to 1. So the antiderivative right here will be T squared over 2. And this is actually 6T to the 5th. So if it's 6t to the 5th, you add 1 to the exponent, so that's going to be t to the 6th divided by 6, so it's actually plus t to the 6th. And then evaluate that from 0 to 1. So that will be 1/2 plus 1 when you substitute the 1, and then of course the 0 will contribute 0. So 1.5 or 1.5 units of work, foot-pounds or newton meters, whatever the units are. Then let's try one a little more challenging. Example number 4. So the force is given by this vector field, xy, comma, xz, comma, zy. So then find the work done along the line from 1, 1, 0 to 2, 3, 8. So since this is a line segment in 3 dimensions, we first need to find a vector that tells us the direction that that line goes. So subtract 2 minus 1, 3 minus 1, and 8 minus 0. And then we can do the parametric form of that line. So that would be 1 times t, y would be 2 times t, and z would be 8 times t. And then we can just put the point 1, 1, 0, like that. And when t equals 0, this is going to be 1, 1, 0. So that means that t is going to go from 0. And then right here, I could look at this one, and t is going to have to equal 1. And if I plug in a 1, this is going to be 2 plus 1 is 3. And if I plug in a 1, 1 plus 1 will be 2. So the limits of integration are going to go from 0 to 1. Okay, so it's going to be the work equals the integral from 0 to 1. And then for the force vector, we need to put x times y to replace this part. So we have t plus 1 times y, 2t plus 1. Then x times z, so this one times this one, so that would be 8t times t plus 1. And then z times y, so multiply these two. 8t times 2t plus 1. And then this is our function, so we need the derivative of it. And the derivative of it would be 1, 2, 8. Or in other words, this vector right there. Okay, now I need to do some algebra. Like multiply this out and then dot product, so multiply it by 1. So when I multiply this out, there's going to be 2t squared, then 2t and one more t, so plus 3t, and plus a 1. Now multiply this out and multiply that by 2. So that actually means 2 times this, so that's 16t. So there'd be 16t squared. And then take that 16t times 1. And then finally, dot product this one with this one, so that's 64t. And 64t times 2 is 128t squared. And then this would be 64t times 1. And then, are there any like terms? So there's squared, squared, and squared. So that would be 144, 146 t squared. And we have t, t, and t. So this one and this one would make 83 plus 83t. And then for the constant, there's a plus 1. So it's going to be 146t cubed over 3 plus 83t squared over 2 plus t evaluated from 0 to 1. So when you substitute the 1, that's going to be 146 over 3 plus 83 over 2 plus 1. And the 0 will be 0, 0, and 0. So that means this is the amount of work. (146) divided by 3 plus 83 halves plus 1 equals this many works. Okay, so 2 more examples. So of course, I checked the homework and they did one like this. Evaluate this line integral. It's going to be x times y dx plus, over the same curve, integrate x plus y times dy. And the curve is just a simple parabola. And then it's going from this point, -1, 1, to this point, 1, 1. And it needs to go this direction. Well, first of all, how do we get the parametric curve for a parabola? Well, a parabola like this would be just y equals x squared. So -1 squared equals +1. 1 squared equals 1, so that's the parabola. And then I could use the parameterization that I'm just going to let x equal t and then substitute that right there. So y equals t squared. And x has to go from -1 to 1. So it should be that it goes from -1 to 1. But before I start doing more math, I want to check and make sure that part's right. So x equals t, and this one is t squared. Change the window, go from -1 to 1. And then I could zoom this in a little bit. So not only does it need to be the parabola, but it needs to be going this direction. So graph it. So that one a little bit fast. I'm going to change this to 0.02 so it'll slow down. Okay, so it went in the correct direction, from left to right. Okay, that's all good. Now what about this part? So this is just saying substitute these two things for x and y, and then put the derivative of x. So multiply by the derivative of x. So this will be integrate from -1 to 1, multiply the x times the y. So that's going to be t cubed. And then times the derivative of this, well, dx would equal just dt, 1 dt. Now move over to this integral, and it now says add the x and the y. And then what about dy? So take the derivative of y, that would be 2t dt, with t going from -1 to 1. So the antiderivative here will be t to the 4th over 4. And this would be 2t squared. So when you integrate 2t squared, that'll be 2t to the 3 over 3. And this will be 2t cubed. So that would be 2t to the 4th over 4 when you integrate it. And I guess I could have even combined like terms. I think I should do that. So that would be 1/4 and 2/4, so that's 3/4 for t to the 4th, plus 2/3 for t to the 3rd. And then evaluate from -1 to 1. Substituting the 1 means that's going to be 3/4 plus 2/3. Now substitute the -1. When you substitute the -1, this is going to get rid of the negative. It'll just give you a 3/4. When you substitute the -1 right here, -1 cubed is -1, so this will be -2/3. Which means this says 3/4 minus 3/4, so that is gone. But then this will be 2/3 plus 2/3, which equals 4/3. So now for the last idea of this section. Suppose that you have some curve C, and then capital F in this case is going to be the velocity of some fluid. Could be water, let's just say water. So this function, this vector valued function, is going to tell you the velocity of the water. So let's say that you're going along this curve right here, and there's water flowing all around you. And then you find the tangent vector going this direction. You could also find the normal vector going perpendicular to that. Okay. Now suppose that you integrate the velocity dot product with the tangent over an arc length. So that's basically saying as you're going along this curve C, then this t is telling you what direction you would be going at that particular point. So you'd be going that direction. And if this is the velocity of the water, and then this tells you the direction, and then you add that up, then that's the total amount of water that is going this direction along this curve C. So this is called the flow. Now, if this C was a closed curve, then instead of the word flow, it would be the circulation. But a more general term is the flow. So how much water is flowing along this direction C. Now suppose that you take that capital F and dot product with the normal vector, and then you integrate with respect to arc length. So that would be a situation where like this, let's say, is a net that somebody dropped into the water and it goes straight down, but that's the curve of the net. And then this would be the water flowing across the net. That's called the flux. So the amount of water that's flowing across the net is the flux, and the amount that's going in this direction with C, that's the flow. Where this is the tangent vector, and this is the normal vector. So for example, number 6, and I'm going to keep the function fairly simple. So capital F is y comma z comma x. That's giving the fluid velocity. And then the path that we're concerned with is a circle. So that's going to be sine of t cosine of t at a height of 1. So basically just go up on the z-axis, a height of 1, and then have it make a circle. So then, part A, calculate the flow. Well, this is a closed circle, so it's actually the circulation. So the calculation is the same whether it says flow or circulation. It's just that this happens to be a closed circle. Oh, I forgot to say, because it's going from 0 to 2 pi. So it's the full circle. So we could do the integral of the f dot product with the t ds. Or there's another way to do it, and that is the tangent vector comes from the derivative. Okay, so we're going to need to substitute this for y, this for z, and then this for x. So we'll be integrating the dot product of, first of all, y, so that's cosine of t, then z, so that's a 1, and then x, so that's a sine of t. And then dot product that with the derivative right here. So the derivative of sine is cosine, the derivative of cosine is negative sine, and the derivative of 1 is 0. And then we're going to integrate from 0 to 2 pi. So the dot product, that's going to be cosine squared. This will be 1 times negative sine. And then this will be 0. So in order to integrate cosine squared, I need to use the trig identity that it's 1 plus cosine of 2t divided by 2. And then find the antiderivative. So for this part, that would be 1/2 dt, so that's going to be 1/2 t. For this part, the antiderivative for cosine will be sine of 2t, but because of this 2, I'm going to have to divide by 2. So it was already divided by 2, I'm dividing by another 2 because of the chain rule. And the antiderivative for negative sine will be positive cosine. That gets evaluated from 0 to 2 pi. So this, when you substitute 2 pi, that's going to be 0. And this is also going to be 0. So this drops out, does not actually contribute to the problem. Then sine of 2 pi times 1/2, so that's going to be pi. When you substitute the 2 pi in here, cosine of 2 pi, that's going to be 1. Now substitute the 0. So that's 0, and cosine of 0 is 1. So then the positive 1 and the negative 1 cancel, so that means that the flow is equal to pi. Now what about the flux? Part B. So still using the same function and still using the same shape. What about the flux? So flux, like I said, is if you have a shape, and so you have some shape like this curve right here, and then water is flowing and it flows through that, then how much water in total is going to flow through that shape? So that's going to be integrate f dot product with the normal vector with respect to arc length. So let's see, the normal vector. First of all, find the tangent vector. In fact, the unit tangent vector. So take the derivative. So that's going to be derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of 1 is 0. And to make this a unit vector, you divide by its length. But its length would be the square root of cosine squared plus sine squared plus 0 squared. And since cosine squared plus sine squared equals 1, its length is 1. So divide this by 1. There, I did it. Now to find the normal vector, take the derivative of that. So the derivative of cosine will be negative sine. Then the derivative of negative sine will be negative cosine. and the derivative of 0 will be 0. And then divide by its length, which is going to be a length of 1. So that means that this is already the normal vector. Okay, so once again we need to do the substituting. So this gets replaced with y. We're still going from 0 to 2 pi. So capital F function would be y, which is cosine of t. The middle one is z, so that's a 1. And then the last one is x, so that's sine of t. And then dot product with the normal vector. And then integrate with respect to t. So in this case, we would have negative sine times cosine, or negative cosine times sine, whichever. We would have 1 times negative cosine, and we would have sine times 0. Now to integrate this first one, you could let u equal cosine, in which case the derivative is negative sine. So basically that's just integrating u du, which means that it's cosine squared over 2 is the antiderivative. And if I check my work, take the derivative, so the 2 will go in front, and then it'll cancel this 2. It would leave cosine, and then because of the chain rule, you take the derivative of cosine, which is negative sine. And for this one, the antiderivative is going to be negative sine of t. Evaluate that from 0 to 2 pi. And I need another pen. So with 2 pi and also with 0, both of those are going to make sine equal to 0. So that is gone. Now cosine of 2 pi, that's equal to 1. So this is going to be 1 squared over 2. Minus, what about when you put a 0? When you put a 0, that's going to be 1 over 2. So that means that the flux is 0. Now what that means is you're going around a circle of radius 1. And because of the function, then some water could be flowing in and some water could be flowing out. And basically, however much is flowing in, the same amount is flowing out. And so the total amount of flux is 0.